So, welcome to lesson 35 of the course Industrial Automation and Control. Today, we will look at the other two kinds of motors which are used in industrial automation, namely step motor drives and Bldc drives. Bldc stands for brushless DC. So, looking at the instructional objective, we are going to, after this lesson, one should be able to describe constructions and principles of operation of stepper motors. There are interesting constructions, and describe how a motor has to be excited in its stator. So, we will describe how these are to be excited. They are generally excited in a switched sequence. Then we will describe means of increasing resolution and speed for stepper motor drives. Stepper motor drives are stepper motors move in discrete steps generally. So, you need to increase its resolution, so that it can move in small angles, and the smaller the better, and it also needs to move fast when you are trying to move something as fast as possible. So, there are certain techniques which are done to increase the resolution and the speed, and explain the principle of operation of Bldc motors. Then we will come to Bldc motors and explain the principle of operation, and we will see interestingly how by using power electronic switching we can make a DC motor, we can make a motor which is basically like a synchronous motor, appear like a DC motor and be controlled like a DC motor. So, we will explain why it is called a DC motor, although it is you could say that it is actually a synchronous motor. Then we will describe control configurations for the Bldc drives, right. So, we first look at step motor drives. There are generally two kinds of step motors. One are called the variable reluctance motors, or the VR motors. So, you have these variable reluctance motors. Let me choose another pen. So, you have these variable reluctance motors, and you have these permanent magnet motors. So, this is the motor stator, the part which is stationary, and this is the rotor. This is actually the rotor has many more teeth, and it is circular looking, but just to explain the principle, I have drawn it as if it's like a cross, so that it has 4 teeth, and we have also drawn it so that it appears that it has 3 phases. So, this is these 2 windings and these 2 windings is one phase, and these 2 windings and these 2 windings is another phase, and here we have not shown coils, there will be another phase. So, it has 3 phases and it has 4 rotor teeth. Now, the principle of operation is exactly like that of an not a permanent magnet motor, but an electromagnet, right. So, this rotor it is made of iron. So, when you excite, let us say, phase A, and you create, let us say you have n poles here. Suppose you have created an n pole here and s pole here, that will depend on the sense of the currents that you are sending. So, suppose you have created an n pole and an s pole, then what will happen is that these 2 magnets will actually attract the rotor, and suppose the rotor will be aligned here. So, this yellow position is for a particular case when these 2 phase A, let us say, is excited, and so the rotor is now aligned with this. Why is it aligned? Because it will align itself so that there is the least reluctance of the flux path, right. So, what happens is that so now as you can see that the reluctance of the flux path for different angles of the rotor are actually different. Say if the rotor was, let us if the rotor was along just inclined as shown by the pink rotor, then the reluctance of the flux path for this faced by these two coils would have been more. So, the reluctance of this path actually depends on the position of the rotor. That is why it is called a variable reluctance motor. So, for any set of phases excited, the rotor will assume that position where the reluctance of the flux path is the least, right, it will come to that position. So, now suppose phase A is excited and the motor has come. So, if the motor previously was in the rotated in the left position, when you excite phase A and create, let us say, a north pole and a south pole here, then what happens is that the rotor will rotate and will get aligned, right. Once it has got aligned, you can then excite phase B. Now, again if you excite, or maybe what is shown here is that suppose this is phase C. So, you excite phase C, right. So, when you excite phase C, then look at the, so now this is going to be an N pole and this is going to be an S pole here. So, this magnet is now going to be attracted towards this and it will assume this position showed by the pink line, this position, let me mark it by green. So, it will assume this position, right. So, you can understand that by first exciting this and then exciting this, you have turned the rotor by an angle. So, if you go on applying, now after B, if you apply a pulse sequence C, then what will happen is that this will get pulled towards this and this will get pulled towards that, and therefore, it will assume another position. So, it will again rotate. So, you see that every time if you do it in a sequence, then every time you are exciting another winding, the motor rotor will rotate by a definite angle, right. That is why it is called a discrete, that is why it is called a step motor, because every time you apply a voltage, it is a DC voltage to a winding, the motor steps, the motor rotates by one step, right. And you can easily calculate the angle by which it will rotate. For example, in this case there are the angle between this and this axis is 60 degree, while this angle is 90 degree. So, actually what will happen is that if this rotor was here, then it will rotate by the it was previously aligned here, then if you excite this and take off the excitation here, then it will rotate by this angle, right. So, correct. Actually what will happen is that you see actually the opposite will happen. What I said is not exactly correct, in the sense that you see when you excite this is an electromagnet, right. So, when you are exciting this, it is in this position. So, this the pole, the angle between this and this will be actually 60 degree, while the angle between this axis and this is actually 30 degree, because it is 90 minus 60. So, actually what will happen is that this pole will get pulled in. So, because it is closer, so this pole will get pulled in, and so the motor will actually rotate by 360 degree by 6 is the angle between this phase and this phase, and 360 degree by 4, because there are 4 rotor teeth. So, each rotor teeth is actually separated from the other mechanically by 360 by 4 angle, which is 90 degree. So, this motor will actually rotate in the clockwise direction. If you first excite this, then excite this, then the rotor will rotate by in the clockwise direction by 30 degree. So, it will rotate 360 by q minus 360 by rather minus 360 by q plus 360 by nr. So, in this case it will rotate by 30 degree. Now, if you so in this case what will happen, nr is 4 and q is 3. So, it will rotate by 30 degree. Now, this is the way a variable reluctance motor works. On the other hand, there is another kind of motor which is called a permanent magnet motor, in which the rotor actually has some permanent magnets. So, these permanent magnets we will see can be fixed to the rotor in various ways, but now previously this was not a permanent magnet, it was just a soft iron rotor. So, it was getting attracted. On the other hand, now you have put magnets here with fixed poles N, N, S, S. So, now what will happen is that if you create an N pole here, then obviously the S poles will now get attracted towards it, and the rotor will actually assume this position. Now, if you create an N pole here and an S pole N pole here, and so this is N N and this is S S, then what will happen is that this S pole will get attracted towards this N, this S will get attracted towards this N, similarly this N will get attracted towards this, and this N will get attracted towards this. And not only that they will get attracted towards this, they will actually be, if you excite actually what will happen is that if you excite it, this will also push it. So, then what will happen is that this rotor will actually rotate, and then this N pole will get aligned with this S pole, while this S pole will get aligned with this N pole. So, the motor will step by 45 degree, right. So, this is the way a permanent magnet motor works. Basically they are absolutely similar, only thing is that there are certain advantages and disadvantages between these two. For example, it is difficult to create, as we have understood now that the resolution, that is the step angle, which is the smallest angular resolution that you can have for a step motor, depends on the number of stator phases you have and the number of rotor teeth or the number of rotor poles that you have. Now, you see how many number of stator phases you can have, or how many stator teeth you can have, and how many rotor teeth you can have, that actually depends on the motor size, because for a given size there is a certain, you cannot create more number of poles than a certain number because of mechanical and spatial constraints, right. So, it turns out that with variable reluctance motors you can have more number of rotor teeth than you can have poles on the rotor. So, therefore, the resolution of permanent magnet motors is generally less than the resolution is less, means it actually steps through a larger angle than in the case of a variable reluctance motor. But on the other hand, you can see that if you do not excite, that is if you this motor actually does not have a lock in torque. So, generally this motor is free, but here you have NS NS. So, this motor will actually lock to this, even in the unexcited condition this motor will actually lock to this position. So, therefore, you have a lock torque available, and till you get excited, till you change your excitation sequence, the motor will not rotate, but will hold the position. So, this may be useful in certain applications. Okay. So, moving on, now how do we excite the stator phases? Oops. Right. So, you have, suppose you let us take a two phase case. So, we have two coils A1 A2 and B1 B2, and I am showing them basically you either have you assume that in the same figure that either you have Q1, you have Q3, you have Q2, and you have Q4. So, assume that for the A1 A2 coils you have these 4 switches, and similarly you can have another circuit in which you have the B1 B2 coils, in which you can have Q5, Q7, Q6 and Q8. Okay. So, now why these switches? Because you can see that in the switching sequence you want to create north and south poles, right. So, if you want to create north and south poles, you need to see the coils are wound already. So, you need to send currents once in this direction and the other in another time in another direction. So, you need to have a bipolar excitation. So, what we are doing is that we are, so you see if Q1 is on and if Q2 is on, then the current plus, so the current will be flowing in this direction, and on the other hand if Q4 is on and Q3 is on, then the current will be flowing in the other direction. So, you can with this circuit, with this simple circuit, you can switch on and switch off currents, I mean reverse the sequence of currents to create either a north pole or a south pole. So, now we will see what is the sequence in which we need to drive these. So, imagine this case that you have these phases A1 A2 and you have these phases B1 B2, right, and you have, we are just for simplicity we are assuming that we have only one pair of rotor poles, right. So, what happens is that, so we the switching sequence, like for example first you will do is that in the first place you will sequence switch Q1 Q2, oops. So, you will switch Q1 Q2, let me change the color. If you switch Q1 Q2, then the rotor will get aligned in one direction. Then in the second step you will switch off Q1 Q2, this you can do, this is one strategy, and you switch on Q3 Q4, right. Similarly, in the next stage you can switch on, you can switch in the next step, third step you can switch off Q3 Q4 and you can switch on Q5 Q6, and in the last stage you can switch on Q7 Q8 and switch off Q5 Q6. So, then you are the motor rotor as we are saying will rotate, right. Now, this is called full stepping, where one phase is actually excited at a time. So, the motor rotates by one angle. Now, we will see that we are always interested in trying to make to be able to make the motor rotate through smaller and smaller angles. So, what we are doing is now look at this. So, there is something that we can do to make it rotate through a smaller angle. So, you see in case of full stepping we were once making this N, this S, and then switching these off and then making this N and this S. Okay. So, it will rotate, first it will get aligned through this, then it will get aligned through this. Actually it gets aligned through a much smaller angle, since we are only drawing 2 pairs of stator magnets and one rather 2 stator magnets and 1 rotor magnet for simplicity. So, it appears that the motor is rotating 90 degrees. Actually it will not rotate 90 degrees, it will rotate by an angle which is dependent on the number of rotor teeth and the number of stator teeth, which is generally much larger than what is shown here. But to understand the principle, suppose we from this position, that is initially N and then S, we make, so this was S attracted to N and this was N attracted to S. Now, if we make this N, keeping this N and S, if we make this N and this S, then what will happen is that this rotor we will assume a position where it will experience equal pulls from these two sides, and this will experience equal to pulls from these two sides, and it will see that now it has rotated through. So, it will assume another equilibrium position which is midway between the two poles. So, by doing this we can make it rotate through half the angle. That is why this is called half stepping. So, now how do we have to excite this sequence for half stepping? So, for half stepping what we have to do is, see, first we have Q1 Q2 on, next we have Q1 Q2 and Q3 Q4 on, right. Next we will have Q3 Q4 on, and then keeping this on, now then we will make only Q3 Q4 on. So, in the third cycle we will have this and we will switch this off. After we switch this off, in the fourth cycle what we are going to do is that we are going to keep this and we are going to switch Q5 Q6 on, okay. So, we are going to have both in this cycle. So, it will rotate by another half. In the next cycle, which is shown in the next diagram, so in the next cycle, which is the fifth step of the cycle, so in the next cycle what will happen is that we had Q3 Q4 and Q5 Q6 on, then we will have only Q5 Q6 on, okay. After having Q5 Q6, then we will have Q5 Q6 and Q7 Q8 on, right. So, you see that we are actually exciting. So, this is exactly what we are doing. We are trying to first excite one coil of one phase only, then we are exciting this and this, so that the rotor moves to half, then we are switching off this excitation so that the rotor gets completely aligned with this one, then what we are doing is that we are changing the polarity of this, so that now the rotor, so we are first creating a field like this, then we are creating a field like this and like this, then we are creating a field only like this, then we are creating a field which is like this and like this. So, you see, first in here the resultant field is like this, next the resultant field is like this, next the resultant field is like this, and then we will keep only this and so on. So, the rotor gets every time aligned with the resultant field of the two stator coils. So, basically that is happening, very simple. And we can understand that the if you have ns number of, if you have ns number of stator teeth, then each phase is separated from the other by 360 degree by ns. If you have the rotor pole pitch as nr, then it is 360 degree by nr for the rotor pitch, rotor tooth pitch, and the rotation for full stepping is theta r minus theta s. Generally theta r is less than theta s, so because it is a smaller. So, you have theta r minus theta s, and for half stepping it is theta r minus theta s by 2, right. So, then you will get generally, I mean often nr is chosen as ns plus or minus ns by q. So, if you do that, then you will get ns by rather 360 degree by q n r as the pole pitch, as the step angle. So, this is the basic principle of operation. If you look at the equivalent circuit per phase, then it is just a coil. So, it has a resistance. So, you are exciting it by a phase voltage, and there is a resistance, there is an inductance, and there is a back EMF, right. So, that is that is the induced EMF. So, if you see the equations, then if the motor is rotating continuously, then the phase back EMF induced is actually proportional to omega, because the flux, it is a motor. So, when it is crossing the coil, the flux is getting linked. So, it is Ke into omega, and for variable reluctance motors, the what is happening is that you see that the rotor is rotating. So, as the rotor is rotating, two things are happening. First, the current itself is changing and the inductance is also changing. So, both things are happening. So, therefore, you have this is the normal resistive drop, V phase equal to R phase into I phase, plus you have an L di by dt term and you have a I dl by dt term, because L is also changing, I is also changing. So, it is basically d dt of flux linkage is Li. So, it is d dt of Li. So, that is I dl dt plus L di by dt. So, it turns out that dl by dt you can write as d theta by dl by dt, you can write as dl by d theta into omega is d theta by dt. So, then you have L di by dt and then I dl by dt. So, and this is the drop in the inductance and this is the induced EMF in the coil. Now, what happens is that so now in a variable reluctance motor, you see that the dl by d theta is between two rotor. Suppose you have a rotor tooth pitch and you have a stator coil here, right. So, you have a stator coil here. So, what happens is that as the rotor is rotating, suppose the tooth was here, sorry, oops, this is not the eraser, this is the eraser. So, coming back, so what happens is that you see as it is rotating this way, initially dl by d theta is positive because inductance is increasing, and after one rotor pole pitch dl by d theta will be decreasing. So, you have dl by d theta during this phase, dl by d theta is positive and during this phase dl by d theta is negative. So, the torque is half I square dl by d theta, torque is half I square dl by d theta. So, you see that the torque and dl by d theta actually changes, dl by d theta is positive, but it is not constant. So, it first starts increasing slowly, then it increases at a high rate, then it falls. So, over a rotor pole tooth pitch, the torque generated varies like this, right. So, now what is going to happen is that how are you going to switch the phases, when? So, you see that initially you switch phase 1. So, this rotor torque is positive. So, the rotor moves now and then the rotor torque will fall. So, unless you change the excitation to now to phase 2, the rotor torque will actually turn negative and it will if you maintain the phase excitation, then the rotor will rotate and then will come back because it has a negative torque. But by the time this torque falls, you have switched on phase 2, right. So, now with respect to phase 2, the same rotor tooth with respect to phase 2 now has a positive torque. So, now it will switch on to phase 2 and will traverse, then when when this one will tend to be negative, then you switch on phase 3, and then now with the same tooth with respect to phase 3 will again have positive torque. So, as the rotor torque tries to reverse, you are switching on another phase, so that with respect to that phase this rotor tooth has a positive torque, and this is happening to all the rotor teeth. So, therefore, you are maintaining an average positive torque and your motor is rotating. So, this this decides that at what should be your switching frequency. So, the principle is that the rotor torque on the rotor tooth should not become negative. So, this is this is some expression which shows that which shows that the inductance is varying as there is a DC component and there is a pulsating component, like I was showing, and then dl d theta is actually a sinusoid. So, the torque is also a sinusoid, right, and electromagnetic torque is half I square dl d theta. So, it turns out that these are the expressions for the permanent magnet and the oh, I do not know why this happened. So, these are the torques generated by the permanent magnet motor. In the permanent magnet motor, flux is constant. So, and so this is the torque generated on the permanent magnet motor, and this is the torque generated on the variable reluctance motor. And finally, what will be the torque generated? So, the total torque is going to be, total torque is T, which is the electromagnetic torque generated like we discussed, and that has to be balanced by the load torque, and the difference in these two torques will actually accelerate or decelerate the machine, or get some of it will actually get absorbed in the friction. So, you can see that this torque itself is actually a function of theta. So, this is actually a nonlinear differential equation, and therefore, this system is actually nonlinear. But anyway, we are not getting into exactly the design of a controller. So, this just shows that how the motor, its principle of operation. So, variable reluctance machine, since it is an electromagnet, so we do not need to, and it is always on the principle of attraction, because the magnet is because the rotor is actually an iron. So, therefore, with you can do with an unipolar drive, and you can achieve smaller step angles because you can have more number of rotor teeth. On the other hand, with permanent magnet machines, you have a lock-in torque, as we said, but you tend to have a larger step angle, and you also have a lower torque to inertia ratio, and you require a bipolar drive. So, these are the the trade offs. Only good thing is that nowadays very good permanent magnets are actually being available. So, you can have very high field strength in these machines. So, that again as these are some comments, but probably during that time they used to use Alnico or something like iron magnets, but now people use rare earth magnets. So, this lower torque inertia ratio concept is probably not valid. Now, we worry about what else we can do to increase the resolution further. So, we have seen that the resolution is depending on the stator pitch and the rotor pitch and the difference in that. So, now there are actually various concepts. So, one of the concepts is that you have what is known as a hybrid motor. So, in a hybrid motor, you see these are the two caps, this is one cap and you have another cap at the two ends, and in between you have a magnet, right. So, you see these are iron caps. So, this thing itself acts like a pole shoe with some teeth, and then you have a stator. Now, you see what happens if you see the end views, then you will find that. So, if you see from one end, then on one end you have this is one cap, and then this is the other cap, right. So, you have the two caps, and on two caps you have rotor teeth, right. So, let's go to the next diagram. So, you have two caps with rotor teeth, and you have equal number of rotor teeth on both the caps. Only thing is that they are slightly offset, why they are offset. So, what happens is that so they have the same number of teeth, but they are slightly offset in such a way that when one tooth, so this is for one cap, say cap 1, when one tooth will align with the stator tooth at one end, the other teeth will actually align with the slot. So, this aligns with tooth and this aligns with slot. So, what happens, and you see this is S and this is N, because there is an internal electromagnet in that. So, now what you do is that when you the first time, that is, so you make it N and S, then the S pole will align with it, and this will be in the middle and they will repel each other. So, they will try to be at the maximum possible distance. So, it will align with the slot. Next time you make this one S and this one N, just opposite will happen, this N will get pulled in and this N will get aligned with the tooth, and this S, this when you make this this N, right, this is N and this is N and right. So, when you make this is S and this is S, because they are in the same phase, see the stator is only one winding. So, then this S will now rotate and will get aligned with the slot, this will assume this position. So, in effect the rotor has moved by half the slot pitch. So, you see that it is, so you have the same kind of excitation, but you can just by having a hybrid motor which utilizes both the principles of rotor slots and one strong electromagnet. So, you do not have to have so many magnets. So, you can have half the phase angle, and this is actually called a so this is one principle. The same principle, similar principle occurs actually in multiple stack motors, which is written here. In a multiple stack motor, actually what happens is that the stator has multiple windings. So, you see, so it has one stack which is one set of stator windings, then you have another stack which is another set of stator windings, then you have another stack. So, the motor tends to be long. Now, what happens is that, and you these rotor slots, so the rotor slots, so you are going to have some rotor slots here and some rotor slots here and some rotor slots here on this shaft, and these rotor slots are actually slightly offset from each other. So, the rotor teeth on the first rotor stack and the rotor teeth on the second rotor stack are slightly offset. So, when you excite the first stack, the teeth get aligned with the first stator coils, first set of stator coils, then you switch it off, or if you are doing half stepping you can also keep them on. So, if then you after you have excited this stack, now you excite the other stack. So, now since the teeth are slightly offset, so then now they will further rotate and they will get aligned, then you excite the other stack. So, you see actually the by creating multiple stacks and multiple rotors, you are actually dividing the overall angular resolution into the further dividing it into the number of stacks. Okay. So, this is happening now. Similarly, you can do a similar thing by doing what is known as a micro stepping. This is another technique where you can actually do current control. So, if you have a two phase hybrid motor, then you can actually simultaneously excite, for example, you can send a current IA through the first phase and create a torque TA and create a torque TB through by sending current IB, and you can control these currents but by a simple switching mechanism. So, if you control these currents and if you change these currents, then the angle will get actually that is the torques generated on the through side will get generated by this angle theta, and then the motor will rotate by an angle which can be controlled by these currents Ia and Ib. So, by having more complex switching, you can actually create even smaller degree motion, but it requires precise control. That is why it is called micro stepping. Okay. So, that is this way that you here. So, this is the current I. So, you do not want the current to increase by more than I, right. So, whenever, so this is your reference current where you want to maintain the current in a phase. This is the actual current. This current, whenever you switch it on, the current starts to build up. Whenever you switch it off, the current starts to fall. So the actual current in the winding is actually always increasing or decreasing, and when it increases by a certain amount. So when you switch it on, say when you have switched on the winding voltage, so the current starts building, and then when it crosses a certain limit, then you switch off one of the switches. So T1. So you can see T1 by seeing the previous one. So you initially you keep T1 T2 both on, and then you switch off T1. The moment you switch off T1, the inductor will start driving current through this loop for some time, because it has some magnetic energy and it does not allow instant reversal of current through itself. So therefore the current will continue for some time, but it will fall in magnitude, and therefore the current will fall. So you switch on T1 and T2, and then you switch off T1. The moment you switch off T1, current will fall. Again, when the current falls too much, then you again switch on T1. So when you switch on T1, so current will fall, then again current will rise, then again. So by doing this continuous switching, you can actually maintain a particular current in a phase, and then as we have seen that you can make the motor rotate by a certain angle by controlling the currents in the phases. So this is the basic idea of micro stepping. Now it turns out that you have to, generally when we are using a motor, we want to move it as fast as possible. So it is not that, see, if you are giving pulses slowly, then what will happen is that you excite one phase, rotor will come and will stand still. So it will actually stop at that position. It might excite because of its inertia, it might give a little overshoot. So it might give a little overshoot, but it will stop. But if you let it stop and then excite, then you are taking more time, right. So you do not let it stop, but you rather, when it has come to a certain point, when the position, from that position it can be pulled in by the next phase, then you excite the next phase, so that it even before it stops, it actually moves to the next position. So this is called slewing. So the rotor never comes to stop, but continuously starts rotating. This is called the continuous slewing mode. So you actually little bit advance your pulses to the phases, so that the rotor does not come to a stop. Oops. So if you see the torque speed characteristic, we will see that when one is trying to start the motor, that is when the motor has no inertia, it is not moving, it is actually at rest, then initially you have to start it. You cannot give very high frequency pulses, because if you increase the pulse frequencies, then actually what will happen if you increase pulse frequency too much, that before the rotor can move, another phase will be excited. So with respect to that, since the rotor has not moved, so with respect to that phase, its torque will not be enough to move the rotor. So therefore we cannot just have more and more speed just by increasing the switching frequency of the phases. That is not possible. So it turns out that while we are trying to start the motor, we have to start it slow, so that it when you are starting it, when you are giving pulses at lower frequency, so initially it will come and then it will stop, then you will give the next pulse, so it again starts moving. So you slowly excuse me, slowly start increasing your pulse frequency, so that the motor gradually starts slewing. and you will find that, so its speed is increasing, and while for it, see, for starting a motor you need a larger starting torque, right. So, for starting a motor you have to start from low value and then gradually ramp the pulse frequency, but once it reaches a certain speed, then slewing will start and it has its own inertia. So, it so it can move a certain extent by its own inertia. So, therefore, you can increase the speed further and your torque requirement has also come down to some extent. So, you can increase it further by actually increasing the speed by doing slewing, but if you increase it beyond this slew torque speed characteristics, so if your load torque is here, then you can only excite it by a frequency up to this. If you excite the stator phases at a higher frequency, then this motor will actually stop, because it will actually come down to a lower speed. So, you cannot increase its speed just by increasing the stator frequency arbitrarily. So, this phenomenon is called ramping. While starting on load, rotor should be accelerated gradually by ramping up the pulse frequency to the desired level. Okay. So, yeah, these are so you can have two kinds of drives for stepper motors, either open loop or closed loop. In open loop drive you are not taking any feedback, so you are kind of assuming that every pulse that you have given has been executed by the motor. Obviously, to this assumption will be satisfied when your pulse frequency is low. So, you are moving slowly, this can be satisfied, provided the load torque is not too much. On the other hand, if you want to really move it fast, then you need to know whether the pulses that you are sending have actually been executed by the motor. So, you need to take a speed feedback. So, you can have two kinds of drives. For more precision drives, people use a speed feedback. So, now we will so the advantages are that you have simple feedback control, position feedback may or may not be needed, you can even do without it, and it is cheap. This is the biggest advantage. And disadvantage is that you have steps, you have limited resolution, you have limited torque, you have limited speed. So, these are its limitations. So, typically these are used in applications such as computer peripherals, let us say the textile industry, where the so high resolution is not required of motion and the loads are not high. So, torque is lower. Similarly, some small rating machine tools, small robots, etc., use step motors. But for the most demanding motion control applications, you need BLDC drives, because this can give you very high torque, this can give you infinite resolution and can give you very high speed drives. So, we will first see what are the why BLDC drives are called BLDC drives. This is a very important concept to understand. So, you see that in a DC machine, you have the poles are fixed, right. So, the poles are fixed on the stator, it does not move. So, you have fixed, so the field MMF is fixed in space, it does not move. Now, the armature is excited. So, the armature is a coil, it is excited by current. So, that also creates an MMF. Now, these two MMFs must be perpendicular to generate maximum torque, but the rotor is rotating. So, as the rotor is rotating, its coils are on the rotor. So, therefore, that will also rotate. So, then what will happen if you did not have brush and commutator, then what would have happened is that the rotor would have come and become aligned with the stator poles. Now, so that does not happen, you have the brushes and the commutators. So, as the rotor rotates, since there are brushes and commutators, so the resultant armature MMF is kept perpendicular to the field MMF. So, the rotor is moving, it is running fast to catch up with the stator, but because of the brush and commutator arrangement, its MMF is slipping out and it is staying perpendicular. This is the principle of the. So, the rotor and the stator MMFs are fixed in space. See, but you will realize that for generating torque, you do not need to keep it fixed in space. You need to keep it always perpendicular. Both of them may be actually rotating, it does not matter. Exactly this principle is used in the brushless DC motor. So, in the brushless DC motor, that is why it is called a DC motor, because here, just like a DC motor, the field and the armature MMFs are kept perpendicular, nearly perpendicular, but the field MMF is rotating at synchronous speed with the rotor. See the rotor is rotating and you do not have any brush. So, you have no so the rotor MMF is rotating. So, to keep them perpendicular, what you do is that you sense the rotor position and you also make the field MMF on the stator rotate along with the in synchronism with the rotor, so that they always maintain 90 degree, right. So that is the essence. So, your field MMF rotating at synchronous speed with rotor and stator field also rotating at synchronous speed, and this is achieved by switching, and the angle between the fields can be controlled, and therefore, you do not need any brush and commutator, but you need to see when you will switch which stator phase, that depends on the rotor position, because you want to keep 90 degree. So, you need to sense rotor position. So, you do not need a brush and commutator, but you need to sense the rotor position. So, the principle is very simple, and you have permanent magnet rotors of various kinds. So, you have either surface magnets where the magnets are several magnets are stuck by some means, glue or something, or sometimes you put them in the, if you have this, then there is a chance for high speed cases because of centrifugal forces they tend to get dislodged, while in the, if you have an interior magnet, then you put it inside the rotor iron, and therefore it can rotate at much higher speed. Nowadays they are very important because the magnets are made of ferrite, cobalt samarium and neodymium iron boron. These are rare earths and can create very high flux densities. So, that is the basic idea. Without going into too much, we will see that these are the three stator phases, and they are actually excited by these what is known as this inverter. So, you see sometimes what is happening is that sometimes current is flowing through this, sometimes current is flowing through this, sometimes current is flowing through this, that depends on which inverter legs you are keeping on. So, you see that if you see the next diagram, you will understand that when in the next diagram you will understand, we will go to the next diagram. So, in the next diagram you will understand that how the stator MMF direction is changed. So, if you have the coil A in a certain direction, one terminal positive and the other terminal negative, we call it A plus. So, the MMF is in this direction. If you change the polarities, it will be A minus, this is in the opposite direction. Similarly, you have B plus and B minus, and you have C plus and C minus. So, you see that so when you connect A plus and C minus, because current is flowing in through one and then going out through the other, then the net MMF is actually along this direction. If you now switch off C minus and you excite B minus keeping A plus on, then the MMF will switch in this direction. So, you have made the MMF switch. So, as the rotor is rotating, you also make this switching such that the stator MMF, previously it was in this direction, when the rotor has moved, you make this switching so that the stator MMF will now go into the other direction. So, using this switching, you are actually rotating the stator condition, and then it becomes like a DC motor with both stator and the rotor MMF rotating. So, this is the basic idea, and so we will switch these transistors Q1, Q2, Q3, Q4 in such a manner that whenever the induced EMF is positive in that phase, we will try to drive current through it, because we know that we can generate positive torque if we drive a positive current for a positive voltage. So, we will be delivering power into that phase, and that phase will experience the torque, and the machine can move. So, we are switching these transistors Q1, Q2, Q3, Q4 in such a manner that they always, so you see at some interval Q1 and Q6 are on, then in this interval also Q1 and Q6 are on, and this is off, and in the next interval Q1 and Q2 are on. So, Q6 has been switched off. So, in this way we are actually switching the stator MMFs and keeping always the torque positive. So, we come to a control scheme. So, what we are basically doing is that you see that we want to do, just like in DC motor, we want to do torque control. So, we have seen in the case of DC motors, this is absolutely similar in the sense that we want to, if you have a position control loop, then we have a position reference, and we give a position feedback. Then we have a position controller which gives a speed reference. So it is actually a cascade loop. This we have seen in the case of the DC motor. So now the speed reference is now compared with the speed feedback, and we have seen that the speed feedback actually adds damping and gives very good motion characteristics. Then the speed controller will actually generate a current reference. Now the current reference is similar to the torque reference because the flux is constant and because it is always maintaining nearly perpendicular, right. So now based on the current reference there is a PWM circuit which will actually switch on this inverter to actually maintain a certain amount of current, and that current maintaining strategy is actually very much like our micro stepping strategy, that we whenever the current will switch, so we will actually switch off, and we have seen how we can do this torque control in the case of other AC motors also using an inverter. So we are exactly similar current control is also applied here. So this is exactly the same thing that we are taking. So this is just a speed control loop. So the speed reference is there, real speed, then PI control, then this is a proportionality controller, and then you generate the current references, and then this current reference will actually go to a PWM regulator which will really create the switching to not only to have the current at certain level, will also have the sense of switching such that the MMFs rotate in the proper direction. So this is, we did it in a fast manner, but you can understand that this is exactly similar, and the main key concept is that the MMFs are rotating and you need to keep them rotating as the rotor rotates. So coming to the end of the lesson, we have seen stepper motor construction, principle of operation of variable reluctance and permanent magnet motors, and methods of increasing their resolution and speed of rotation by slewing. And we have also seen the basic principle of operation of the Bldc motor, and we have seen one control configuration of Bldc motors and seen that it is just like a DC motor except for that PWM switching which creates the stator phase to rotate. Coming to the points to ponder, you can compare stepper motors with DC motors and see why one is better than the other and when. You can compare variable reluctance and permanent magnet motors also. What is slewing? So we have discussed this, and why is it useful? Obviously for having more speed. Are Bldc motors DC motors? By construction they are not, but by operation they are made to behave, but by behavior they are like DC motors. So you can either justify or contradict, and explain why Bldc drive is the preferred choice for servo applications, because you can have performance like a DC motor without the problem of the commutator and the brush. You can get very good torque because you get very good magnets. So that is all for today. We have looked at the various motor drives, and from the next lesson we will move on to a new topic. So we have seen the electric actuators used for industrial automation. Thank you very much.